All right, let's dive right in. We're about to tackle one of the biggest, strangest, and honestly most important mysteries in all of science. Think of this as a cosmic detective story, where we're investigating the world of quantum photonics. This is a place where tiny particles of light, photons, show us that the universe is just so much weirder than any of us could have possibly imagined.
And it all kicks off with this one seemingly simple question. A question that actually created this huge rift between Albert Einstein and the founders of quantum mechanics. Here it is. Is the universe out there doing its thing with definite properties, even when we're not observing it? Or, and this is the weird part, does the very act of us looking at something actually bring its reality into focus? This question, right here, is the scene of our cosmic crime.
So that brings us to the first chapter of our story, this massive debate over the very nature of reality itself. You've got common sense on one side, and then you've got the bizarre, almost unbelievable rules of the quantum world on the other.
Okay, so let's meet our two main suspects. In one corner, you've got Einstein's view, local realism. This is basically your gut feeling about how the world works. It says that objects have real, definite properties, like where they are and how fast they're going, whether we measure them or not. And crucially, that nothing can travel faster than light. No secret messages, no instantaneous action. On the other side, we've got quantum mechanics, championed by Niels Bohr. This view says, well, actually, a particle's properties can be totally fuzzy and undefined until the moment you measure them. And some connections can seem to happen instantly, breaking that cosmic speed limit.
To make his point, Einstein's argument basically boiled down to this one really elegant idea. It's called the EPR reality criterion. He said, look, if you can figure something out about a particle, predict its value with 100% certainty without ever directly poking or prodding it, then that something has to be a real, concrete property that was there all along. I mean, that sounds totally logical, right? For Einstein, this was proof that quantum mechanics had to be missing something.
But quantum mechanics had an ace up its sleeve. A piece of evidence so strange that Einstein himself famously called it spooky action at a distance. This, right here, is the smoking gun of our mystery, quantum entanglement.
So what is entanglement? Well, it's a process that links two particles together so they effectively become a single system. You can think of them like a cosmic pair of twins. Whatever you learn about one, you instantly know about the other, even if they're on opposite sides of the galaxy. And it's not like they're sending a signal back and forth. This connection is just built into their shared existence from the start.
So, how does this actually work? Well, physicists love to use this classic thought experiment with two people. We'll call them Alice and Bob. First, you create an entangled pair of photons. Then, you send one photon to Alice and the other to Bob, who could be light years apart. Now, the moment Alice measures a property of her photon, let's say its polarization is up, she instantly knows, without a doubt, that Bob's photon is down. The information didn't travel from her to him, their fates were just linked.
For decades, this whole thing was just a debate, a philosophical argument between these giants of physics. But then, a physicist came along who figured out a way to take this question out of the realm of philosophy and put it directly into a laboratory. It was finally time to put local realism itself on trial.
And that physicist was John Bell. In 1964, he came up with a brilliant mathematical theorem that you could actually test with an experiment. The goal wasn't really to prove quantum mechanics was right. It was to find out once and for all if local realism was wrong. This was the moment our cosmic detective story became a real, live investigation.
Okay, Bell's test is kind of like a game designed to figure out which set of rules the universe plays by. You have Alice and Bob again, and they each measure their entangled particle, getting a result of either +1 or -1. They do this over and over with different settings. Now here's the kicker. If the universe is locally real, Einstein's common sense view, the math guarantees that the correlation score from their combined results can never be higher than 2. But if quantum mechanics and its spooky connection are correct, they can basically cheat this classical limit and get a score that's greater than 2. So the experiment had a very clear line in the sand. And the verdict? Drumroll, please. Experiment after experiment, getting more and more precise over the years, has come back with a value greater than 2. The evidence is just overwhelming. Einstein's common sense, locally real view of the universe is wrong. The universe is officially, certifiably weird. That spooky action is very, very real.
So case closed, right? Well, not quite.
See, for scientists and engineers, proving that reality is fundamentally weird is just the starting line. The next, and maybe more exciting question is, what can we do with all this weirdness? And this is where our story shifts from a mystery to a full-blown technological revolution.
First up, communication. Because entangled particles are so perfectly linked, you can use them to create cryptographic keys that are, by the laws of physics, completely unhackable. Seriously, if anyone tries to eavesdrop on the connection, they would have to measure a particle which would instantly disturb the system and reveal the intruder. Game over for hackers.
And then there's quantum teleportation. Now hold on, this isn't about beaming people around like in Star Trek. What we're talking about is transferring the exact quantum state, all the information of one particle to another particle in a different location. The original is destroyed in the process. We're teleporting pure information, not matter, and the whole thing depends completely on that spooky entangled link.
And of course, there's the big one, quantum computing. Forget the step-by-step process of a normal computer, which is like a line of dominoes falling one after another. Quantum computers create these vast interconnected webs of entangled particles called cluster states. You perform a computation by just measuring one particle, and that measurement instantly ripples through the entire entangled cluster, affecting all the others. This lets them tackle problems with a scale of possibilities that is literally unimaginable for even the most powerful classical supercomputers. So, when you put it all together, what do you get? Well, you get the promise of a future with perfectly secure global communication. You get the ability to transfer delicate quantum information across the planet, and you get computers powerful enough to solve problems in medicine, climate science, and material design that are completely impossible for us to solve today.
So finally, let's just take a quick look at how fast this future is actually arriving. I mean, the journey from a philosophical debate in the 1930s to world-changing technology today has been absolutely breathtaking.
I mean, just look at the pace of this. The very first time quantum teleportation was achieved in a lab was 1997. That's not that long ago. And just over a decade after that, scientists were already building the key components for quantum computers and the basic building blocks of a future quantum internet. We've gone from a mind-bending idea to real, tangible hardware in just a handful of decades.
And so we end right back where we started, with a really profound question. Our little detective story proved that reality is non-local, that things are interconnected in ways that we are only just beginning to grasp. It just makes you wonder, what's the next impossible idea out there that's just waiting for the right experiment to come along and prove it's been true all along?